Hi, hello. This is Professor R.S. Patil. I would like to start from the last lecture. I would like to continue with the last lecture. Before I start the actual syllabus, I would like to remind you whatever the syllabus that I have covered in the last lecture. So, in order to understand in detail whatever the syllabus I covered in the last lecture on psychometry, I please request you to go through my previous video which is uploaded. Okay. So as a formality, I would like to remind you whatever the syllabus I covered in the last lecture. Then we will go to the next syllabus. In the last lecture, we talked about the dry air. So dry air is the air which has no water vapor at all. So practically, it is impossible to get the dry air in the atmosphere. Okay, then we talked about the moist air. Moist air is nothing but the dry air plus water vapor. So in nature, we are finding the moist air. Okay, then so we talked about the moisture. Moisture is nothing but the water vapor. Then we talked about the very important concept called saturated air. I spent lot of time in explaining the saturated air because the all the concept of psychometry is standing on the concept of saturated air. I hope you have followed the concept of saturated air. If you don't followed, if you have not followed, I request you please go through the my previous video and try to understand about saturated air. As formal definition, the saturated air is the air which is having the water vapor which is equivalent to its maximum capacity at that particular temperature, or the saturated air is the air which is having the maximum amount of water vapor at that particular temperature. Then we studied about what happens with the water vapor when saturated air is cooled. Then later we talked about how the condensation or removal of water vapor takes place in the air. Then we talked about what happens with the water vapor when saturated air is heated. Then we talked about how to find out maximum amount of water vapor at particular temperature using the chart. Okay, so these are the concept that we talked about in the last lecture. Now today we are going to a new concept. I hope you are going to follow me and you are going to encourage me and you will take benefit out of it. Okay, so please comment on my video and you can take the output from it. Okay, let's begin with the new concept. So the today's topics, among the today's topics, the first topic is Dalton's law of partial pressure. So this law is basically for gas. Okay, so gas means I talked about there are so many gases are there in the atmosphere, and all the gases together we are calling the dry air. All these gases together we are calling the dry air. And apart from the dry air, apart from all these gases, there is a one more gas. There is a one more gas in the atmosphere, I told you, which has got very important role in keeping us comfort or discomfort. Its quantity in the atmosphere has got very important role, and its quantity will be varied from time to time or season to season or place to place. Okay, that is water vapor. Now we are going to take the two mixture, the mixture the mixture which has got two gases. What are the two gases in the mixture we are considering? Dry air and water vapor. So again and again I am telling you, dry air is nothing but all the gases together, and we are not going to call them individually. Dry air is nothing but all the gases together, and on the other end one more gas is there, water vapor, and we are considering the two gases in the mixture. And this Dalton's law of partial pressure is the gas law, which states that the total pressure exerted by the mixture of these gas, the total pressure exerted by mixture of these gas will be equal to the sum of partial pressure exerted by individual gas. So how many individual gas are there? There are two gas are there, dry air and water vapor. So the total pressure pt is equal to the total pressure of the mixture is equal to the sum of partial pressure exerted by individual gas, that is the dry air and water vapor. So pt is equal to pa plus pv. So this is what the statement of Dalton's law of partial pressure applied to this mixture which has got only two gases, that is dry air and water vapor. Understood? Very simple. That is the total pressure exerted by this mixture of gases is equal to the sum of partial pressure exerted by two individual gases, that is PA, that is partial pressure exerted by dry air, and PV, partial pressure exerted by water vapor. Okay, so this formula or this statement can be applied for any number of gases in the mixture, but in our psychrometry there are only two gases is to be considered. One is the dry air and another one is the water vapor. So we applied the Dalton's law of partial pressure to this mixture. Okay, so formal definition of the Dalton's law of partial pressure is that this is the gas law which states that the total pressure exerted by mixture of gases is equal to the sum of the partial pressure exerted by each individual gas in the mixture. Each individual gas, there are two gases are there. I hope you have understood the Dalton's law of partial pressure. Okay, this is very important. What is PV? It is the partial pressure exerted by water vapor. So the water vapor varies. I told you water vapor is not a fixed quantity. It varies from minimum to maximum. If you consider a particular temperature, if the air has no water vapor, then that is the dry air, and air has got its own capacity to hold the water vapor. It means that a PV, the intensity of PV varies from 0 to maximum. If there is no water vapor, obviously the PV is 0. The partial pressure exerted by water vapor is 0 because there is no water vapor. If the water vapor is the maximum, then the partial pressure exerted by water vapor is the maximum. It means that the PV is also varies from 0 to maximum, as water vapor also varies from 0 to maximum. But the PA, the magnitude of PA will be remains constant because we are considering the dry gases. The gases which are considered as the dry gases is to be remains constant. Okay, so now let's go to the next concept. Now the same formula we are going to apply for both saturated air and unsaturated air. So saturated air, I told you, let's consider 1 kg of air at 18 degrees Celsius. If 1 kg of dry air at 18 degrees Celsius, if it has a 0 kg of water vapor, tell me what it is called? It is the dry air. And the question arises, 1 kg of dry air at 18 degrees Celsius at max, how much amount of water vapor it can hold? The specific answer to that is 0.0129 kg. Okay, now the next question, how much amount of water vapor actually the air is carrying? Its quantity is 0.0121 kg. Then tell me which air it is. Air is having water vapor. Of course, it's the moist air. So moist air, but whether it's saturated air or unsaturated air. So air is having the water vapor which is less than its maximum quantity at 18 degrees Celsius. Obviously, this is unsaturated air. So let us see the another condition at 18 degrees Celsius. And the same 18 degrees Celsius is carrying the amount of water vapor is 0.0129 kg, which is equivalent to its maximum capacity at 18 degrees Celsius. So now tell me which air it is? It is the saturated air. Now we are going to introduce the variable for saturated air and unsaturated air. That I have already done in the previous video. Again I am going to do for your understanding. That is what? Mass of water vapor, mv. How much? 0.0121 kg. Is it right? Yes. So when the same mass of water vapor, when I am going to denote for saturated air, it is mvs. That is mass of water vapor when air is saturated. Tell me mvs is how much? 0.0129 kg. So which one is more? Obviously mvs is more. Mass of water vapor is more obviously when the air is saturated. Okay, so like that, what is PV? The partial pressure of water vapor, PV. This PV is due to mv, means the mass of water vapor is there in the air, water vapor is there in the air. Because of that, there is a pressure created, that is PV, the partial pressure exerted by water vapor. but when air is unsaturated. Same variable that I am going to denote when the air is saturated, that is PVS, the partial pressure exerted by water vapor when air is saturated. Tell me which one is more? Obviously P suffix Vs is more. This in PVS is more because MVS is more. As the water vapor is more, obviously the partial pressure exerted by water vapor is more. Okay, like that, density of water vapor rho V when the air is unsaturated, when the same air becomes saturated, we are going to denote density of water vapor when air is saturated, that is rho Vs. Understood? Now we are going to write the formula for Dalton's law of partial pressure for both unsaturated air and saturated air. For unsaturated air, Pt is equal to Pa plus Pv. But when you write the same formula for saturated air, Pt equal to Pa plus Pvs. Pvs means partial pressure exerted by water vapor when air is saturated. So Pa is remains constant, only Pv changed from minimum to maximum, because the only in the mixture only water vapor will be changed from 0 to maximum. When 0 is there, PV is 0. When maximum is there, PVS is maximum. Okay. So let's go to the next slide. Now, very important definition. So far we used to say that water vapor, but the technical word of the water vapor that we are going to call is the humidity or the specific humidity or the humidity ratio. Okay, this is very important definition. So look at this. What is the humidity or specific humidity or humidity ratio? Specific humidity is defined, it is the amount of water vapor present in 1 kg of dry air. So for the same table that we referred, it is the amount of water vapor present in 1 kg of dry air. For example, look at this. At where is, yes. For example, look at this. At 10 degrees Celsius, at 10 degrees Celsius, the how much amount of water vapor is there? 0.0076 kg per kg of dry air. This much amount of water vapor is there per kg of dry air. This is called specific humidity. Obviously, this quantity will be varied. This quantity will be varied from 0 to maximum. 0 to maximum. But in this table, we have given the maximum quantity of water vapor that can be present per kg of dry air at a particular temperature. So for example, at 13 degrees Celsius, if you take, this is the amount of water vapor in kg. This is the amount of water vapor in kg present in 1 kg of dry air. That's it. That is the meaning of specific humidity. Okay. So what is specific humidity? The amount of water vapor present in 1 kg of dry air, and amount of water vapor you are measuring in kg. So that is the reason. So the unit of specific humidity is kg per kg of dry air. This kg refers to the water vapor, and this kg refers to dry air. Okay, so don't get cancel them, and you cannot say that the specific humidity has no unit at all. So 0.0076 kg refers to the amount of water vapor and per kg of dry air. Okay, so the amount of water vapor present in 1 kg of dry air, that is called specific humidity, and this amount of water vapor may vary from 0 to maximum at that particular temperature. So far we talked about that, and this table is referring the maximum amount of water vapor present in 1 kg of dry air at that particular temperature, okay. So this is called the specific humidity. Let's go to the next. Now same thing, within a 1 minute I would like to reiterate. So this is a saturated air, unsaturated air. This is for saturated air, and and so mv is the mass of water vapor when air is unsaturated, mvs mass of water vapor when air is saturated, pv is the partial pressure of water vapor when air is unsaturated, partial pressure of water vapor when air is saturated, density of water vapor when air is unsaturated, density of water vapor when air is saturated. But now the word new terminology that we learned is the specific humidity. Or specific humidity is denoted by W when air is unsaturated. Specific humidity is denoted by W suffix S when air is saturated. Obviously Ws is more or W is more? Ws is more, because what is a specific humidity? The amount of water vapor present in 1 kg of dry air, and this amount of water vapor will be maximum when the air is saturated. Obviously W suffix S, that is specific humidity when air is saturated, is more than the specific humidity when same air is unsaturated. Okay, I hope you are following me. Thank you. Next, we shall go to the psychometric chart. How the specific humidity lines are going to be identified on the psychometric chart. Please try to understand. So these are the straight line. These are the straight line, that is the specific humidity lines are there. So I have shown there are so many I have shown the specific humidity line. It does not mean that these are only the specific humidity line. In between the specific humidity lines, in between whatever I have shown the specific humidity line, there are some specific humidity lines are there like this. But for your reference, for your reference, I have just shown some of the specific humidity lines. These are the specific humidity lines which are straight and horizontal line, straight and horizontal line. Okay, and this is the scale is called the specific humidity scale. For example, the thing is written here 0.033. The thing is written here 0.019. The thing is written here 0.008. What is this? This is 0.008 kg of water vapor, 0.019 kg of water vapor, 0.033 kg of water vapor present in 1 kg of dry air, present in 1 kg of dry air, present in 1 kg of dry air, present in 1 kg of dry air. Understood? This is the specific humidity scale. For example, 0.027, it is the kg of water vapor present in 1 kg of dry air. Okay, so formal definition of specific humidity is defined as the amount of water vapor present in 1 kg of dry air, denoted by W when the air is unsaturated, and denoted by W suffix S when air is saturated. Okay, and how the in the psychometric chart, how the specific humidity lines are identified? They are, that is the straight and horizontal lines. So whatever the straight and horizontal lines are there, they are specific humidity lines. Okay, so we will discuss more on this. Don't worry, we are not going to make any conclusion or end of the topic. So again and again we are going to discuss about these topics whenever it is required. Okay, now let's move. Now the first derivation we are going to make on the psychometric concept, that is the specific humidity. What is specific humidity? That is the amount of water vapor present in 1 kg of dry air. That is, it is defined as, it is the ratio of mass of water vapor to the mass of dry air. MV is the mass of water vapor and MA is the mass of dry air. It is the ratio of mass of water vapor to the mass of dry air mathematically, because it is, what is ME? Amount of water vapor present in 1 kg of dry air. Okay, now please try to understand. We have the mixture. In the mixture there are two gases are there. One is the dry air and another one is the water vapor, and both the gases are treated as the ideal gas. Both the gas are treated as the ideal gas. That is the reason we can apply the ideal gas equation, that is PV equal to MRT. And if you don't treat any gas is the ideal gas, you cannot apply PV equal to MRT. As dry air and water vapor, they are treated as the ideal gas, so we are applying the ideal gas equation PV equal to MRT. Now the same equation can be written in terms of mass is equal to PV by RT, and I am going to write this mass formula in terms of dry air and in terms of water vapor. That's it. So I am writing the mass formula in terms of water vapor is equal to PV, P suffix V into V suffix V divided by R suffix V into T suffix V. So what is P suffix V? Partial pressure of water vapor. What is V suffix V? Volume of water vapor. What is R suffix V? The characteristic gas constant of water vapor. What is T suffix V? Temperature of water vapor. So in the same way, I am going to write the formula of mass for dry air. M suffix A, mass of dry air, is equal to P suffix A, that is partial pressure of dry air. V suffix A, volume of dry air. R suffix A, characteristics gas constant of dry air, and T suffix A, temperature of dry air. Okay, so I am going to substitute both M suffix mass of water vapor and mass of dry air in the equation number 1, that is W equal to mv divided by mv. This will be the, after substituting, this will be the equation. Now please try to understand, in this equation I am going to cancel, so I will take the next equation. Please look at this equation and this equation. What are the variable that cancelled? I have cancelled the volume of water vapor and volume of dry air. I have cancelled the temperature of dry air and the temperature of water vapor. Now let me know why they are got cancelled. After getting it cancelled, your equation has become the RA divided by RV into PV divided by PA. First of all, I would like to teach you why the volume of water vapor is equal to volume of dry air. How the temperature of dry air is equal to temperature of water vapor. If both the temperature are same, then only you can get cancelled, na. If both the volumes are same, then only they get cancelled, na. Otherwise, how can you get them cancelled? So that concept we will learn. Then we will continue the derivation. Okay. So this is a formal definition. The specific humidity is defined as the amount of water vapor present in 1 kg of dry air, that I already told. The thing that we need to understand, that how temperature of air is equal to temperature of water vapor, how the volume of water vapor is equal to volume of dry air. Please listen here. These are the gases. Together we are calling the dry air. The one more gas is their water vapor. We have taken these two gases in the container as a mixture. Okay. So whose temperature is 30 degrees Celsius. What is the temperature? 30 degrees. Mixture temperature is 30 degrees Celsius. Of course, understood. Then, if the mixture temperature is 30 degrees Celsius, what is the temperature of all the gas? It means that if the mixture temperature is 30 degrees Celsius, do you think that the temperature of dry air is different and temperature of the water vapor is different? As I told, in the atmosphere, all these gases are there. And if I ask you what is the today's atmosphere temperature, if you Google it, it is showing the 25 degrees Celsius. It is atmosphere temperature, 25 degrees Celsius. In the atmosphere, there are so many gases are there. Do you think that all the gases have got different temperature? Like nitrogen has got different temperature, oxygen has got different temperature, argon has got different temperature, water vapor has got different temperature. Does it mean like that? So conclusion from this slide is that temperature of the mixture of gas is equal to the temperature of the individual gas. It means that the temperature of the dry air is equal to the temperature of water vapor is equal to the temperature of mixture. Very simple. Okay, that is why TA and TB gets cancelled. So now let's go to the same gases. In the mixture we have taken the two gases, that is the water vapor and dry air. Okay, so mixture got temperature 30 degrees Celsius. It means that dry air has also got 30 degrees Celsius. Water vapor has also got 30 degrees Celsius. Okay, let us consider if the mixture volume is 1 meter cube. Then what is the volume of individual gas? It means that if the total mixture volume is 1 meter cube, then do you think that the volume of the dry air is different and volume of the water vapor is different? It is not possible, because both the gases have been uniformly distributed throughout the space. That is the reason the volume of dry air is equal to volume of water vapor. If it has to be different, then then the water vapor should be occupied in some region and what dry air should be occupied in some region. Is it like this? For example, like this. Let us make two parts. Here the water vapor is there, here the dry air is there. Like this? Is it like this? No. The water vapor and the dry air is uniformly distributed. That means both have got the same volume, that is equal to mixture volume. So conclusion from this table is that, from this slide is that the volume of dry air is nothing but volume of water vapor, is nothing but volume of mixture. Okay, so that is the reason VA and VV gets cancelled. So let's move to the same derivation. What is specific humidity? The mass of water vapor to the mass of dry air. So why I am applying the ideal gas equation? Because both the gases are treated as the ideal gas. So I have written PV equal to MRT is equal, M equal to PV by RT. M mass of water vapor can be written like this, mass of dry air can be written like this. Both the masses are substituted in the first equation. Here the I am going to cancel volume of water vapor and volume of dry air, and temperature of dry air and temperature of water vapor. So this is a simplified equation. Understood? Now, what is Ra? It is the characteristic gas constant of dry air. What is Rv? It is the characteristic gas constant of water vapor. Now, how to find out this? So, we have the equation. That is, which equation? If you want to calculate the characteristic gas constant of any gas, then the universal gas constant should be divided by molecular mass of that gas. For example, I want to calculate characteristic gas constant of water vapor. Then what is the universal gas? Universal gas constant is common for all the gas. It is fixed 8.314 divided by molecular mass of water vapor, that is 18. So how much you got? 0.462 kilojoules per kg Kelvin. Now in the same way I want to calculate characteristic gas constant of dry air. So the universal gas constant 8.314, that should be divided by the molecular mass of dry air, that is 29, that is equal to 0.286 kilojoules per kg Kelvin, and these two data I will substitute there. 0.286 divided by 0.462. I have kept PV as it is, and but instead of PV I have written PT minus PV. Have you got this? How it has come? Because the Dalton's law partial pressure says that the total pressure exerted by mixture of the gas is equal to the partial pressure exerted, sum of partial pressure exerted by individual gas, that is PA plus PV. Now how can you write PA? PA is equal to PT minus PV. So instead of PA you have written PT minus PV. So the final equation is 0.286. If you divide by 0.462 you will get 0.62. So PV divided by PT minus PV. This is very important derivation. On this there are so many numericals have been asked in the GATE exam, and in academic also you will be asked to prove that W equal to 0.62 PV divided by PT minus PV. It will be asked as a common question. It will be asked in academic also. It's a very important derivation. Please practice once or twice. Definitely you will have perfection in it. So what is W? That is the specific humidity. And what is PV? The partial pressure of water vapor. And PT is the total pressure, and PV is the partial pressure of water vapor. Okay, and if you apply for example, if I ask you to apply the W equal to 0.62 PV by PT minus PV. Okay, so this is what the specific humidity when air is unsaturated. But if I write the specific humidity when air is saturated, W instead of W it becomes WS, and 0.62, and PV becomes partial pressure of water vapor when air is saturated, PVS, divided by PT minus PV becomes PVS, like this. These are very important to differentiate the variables when air is unsaturated and where is air is saturated. Okay. So let's move. Now, so I am going to take the another terminology, that is absolute humidity. We have talked about the specific humidity. What is specific humidity? It is going to measure amount of water vapor present in 1 kg of dry air. Mass of water vapor present in 1 kg of dry air. Okay. But if you take the absolute humidity, same mass of water vapor but present in 1 meter cube of dry air. So, in specific humidity per kg of dry air, you are measuring the mass of water vapor. In absolute humidity per meter cube of dry air, you are measuring mass of water vapor. That's the difference. For example, W equal to 0.0087 kg. What is this 0.0087 kg? This 0.0087 kg is the mass of water vapor present in 1 kg of dry air. So, on the same way, what is this 58.1 kg or gram? 58.1 gram. What is this mass of water vapor present in 1 meter cube of dry air? So what is the unit? Look at this. Why we have denoted to the we have denoted rho to the absolute humidity. Absolute humidity is nothing but the density, because kg per meter cube what? Mass per unit volume. Here gram is taken, but if you keep gram per meter cube or kg per meter cube, it doesn't matter. So absolute humidity is nothing but the density of water vapor. Understood? What is the difference between specific humidity and absolute humidity? Specific humidity is mass of water vapor present in 1 kg of dry air. Absolute humidity is mass of water vapor present in 1 meter cube of dry air. That's it. Okay. So let's move to the next concept. Now this is very important one is the relative humidity. For example, if you Google what is the today's climate condition, then there will be the temperature and there will be the relative humidity, and relative humidity is given in terms of percentage, like that. For example, what is the today's Lonavala climate condition? So it is a 25 degrees Celsius, 30% relative humidity. Then I ask you, what is 30%? What do you mean by 30%? For example, how much marks you scored? Somebody, if I ask somebody, sir, I scored 50% marks, means maybe 100 marks test and he scored 50 marks, so he's saying 50% marks. So in the same way, there's a 25 degrees Celsius temperature is there, relative humidity is 30%. What exactly 30% means? What is 30%? So that you need to understand. First of all, we will make the formal definition of relative humidity. For that, again I take the concept of saturated and unsaturated. What is this? Now I am taking the 18 degrees Celsius dry air. If it is having a 0 kg of water vapor, it is called of course dry air. The question arises, for 1 kg of dry air at 18 degrees Celsius at max, how much amount of water vapor it can carry? That is 0.0129 kg. It's the maximum. Minimum is 0. MV is 0 and MUS is 0.0129. Okay, the question arises, actually how much the water vapor the air is carrying? 0.0121. So you can say MV is 0.0121 and MVS is 0.0129. This air is called what? Unsaturated air, because the air is having water vapor which is less than its maximum capacity. Okay, the same air, let's say the same air 18 degrees Celsius is carrying 0.0129 kg. It means that air is carrying the water vapor which is equivalent to its maximum capacity. So this air is called saturated air. So I already defined what is MV, mass of water vapor when air is unsaturated, mass of water vapor when air is saturated. Then how to define the relative humidity? Relative humidity defined as it is the ratio of mass of water vapor when air is unsaturated to the mass of water vapor when air is saturated. In the same way, we can also define like partial pressure of water vapor PV when air is unsaturated, partial pressure of water vapor when air is saturated. But you can define the relative humidity is defined, it is a ratio of PV by PVS, that is It is the ratio of partial pressure of water vapor when air is unsaturated to the partial pressure of water vapor when air is saturated. Like that, density of water vapor rho v when air is unsaturated, the same variable can be denoted rho vs when the air is saturated. So you can also define the relative humidity in terms of density, that is phi equal to rho v by rho vs, that is density of water vapor when air is unsaturated to the density of water vapor when air is saturated at that temperature. Means, have you got this? These are the three formula can be applied. Relative humidity is defined in terms of three formulas. Okay, so let's go to the, in order to have more clarity on this concept, we'll go to the psychometric chart. This is a psychometric chart. So earlier we learned how to identify the specific humidity lines. Now we are going to identify the relative humidity curves. Look at this. These are the 10% relative humidity, 20%, 40%, बीच में 30%, 50%, 60%, 70%, 80%, 90%, and last one is 100%, which is called saturated curve. Okay, so now try to understand. For example, a temperature, for example, today's condition, the temperature of that particular region is 20 degrees Celsius and relative humidity is 100%. It means what? The relative humidity is 100%. It means the temperature at 20 degrees Celsius, I told you, at 20 degrees Celsius, air has got its own capacity to hold the water vapor. Air has got its own capacity to hold the water vapor. Agree? Since from the first lecture I am telling you, every temperature has got its own capacity to hold the water vapor, maximum amount of water vapor. Like that, 20 degree has got it has got its own capacity to hold the water vapor. When you call the relative humidity is 100%, it means that the 20 degrees Celsius is having the maximum amount of water vapor. 20 degree Celsius air by 1 kg of dry air is carrying maximum amount of water vapor. It means that there is no vacancy at all. It means that air is saturated. There is no vacancy at all. The 1 kg of dry air at 20 degrees Celsius is carrying maximum amount of water vapor. So relative humidity is 100%. It means that there is no vacancy in the air. Air is having maximum amount of water vapor. The air is saturated. In simple word, air is saturated. For example, let us say another condition. The temperature is 15 degrees Celsius and relative humidity is 90%. It means what? It means that the 15 degrees Celsius has got its own capacity to hold. So out of that capacity, 90% is filled. 90% is filled, 10% is vacancy. So still 10% of water vapor you can add. So that obviously if there is a vacancy, even 1% vacancy is there, that air is called unsaturated. For example, if I take a 30 degrees Celsius and 50% relative humidity, it means that the 30 degrees Celsius, 1 kg of dry air has got its own capacity to hold the water vapor. Out of that capacity, only 50% is fulfilled and 50% is vacant. That is, air is unsaturated. Understood? Understood na? So you must understand the relative humidity in terms of percentage. 50% means the 50% of water vapor is filled in the air at that temperature and 50% vacant. Okay, so far in order to define the saturated air and unsaturated air, we were dependent on that table. We used to see at this temperature what is the maximum quantity of water vapor, and we used to compare with how much amount of water vapor the air is carrying with the maximum amount of water vapor. If air is carrying amount of water vapor equivalent to maximum capacity, we used to call saturated air. We used to see if the amount of water vapor is less than its maximum quantity, we used to see less than maximum capacity, we used to say unsaturated. But I told you in the beginning, we need not to remember the maximum amount of water vapor at that particular temperature. It's not possible at all. For each temperature, what is the maximum amount of water vapor? So very simple. In order to say whether the air is saturated or unsaturated, here is the one more data which is available. If relative humidity is 100%, it means water vapor is completely filled in the air, no vacancy to accommodate further more water vapor, and air is saturated. If less than 100%, obviously there is some vacancy. For example, 90%. 90% is filled at 15 degree, 10% is vacancy. 50%, it means 50% is filled at 30 degree, still 50% vacancy is there. Understood? Conclusion from this table is that if the relative humidity is 100%, that is called saturated air. If it is less than 100%, then that is called unsaturated air. Okay. Thank you very much. So I will come back to you in the next lecture. I hope you are enjoying my lecture and you are really taking benefit out of it. Thank you very much.